Hello, I'm Sadia Samreen from 3rd BTech EC. In this presentation, I'll be showing you about how do we optimize neural networks backpropagation using RMS prop optimizer. Initially, to start with, we need to know about what is a neural network and what is backpropagation and how do we do it. In the figure shown one, this figure is a simple neural network with an input layer, one hidden layer and one output layer. Input is given to this input layer. It gets propagated through the hidden layer and then it goes to the output layer and we get the final output. When input is given, it get multiplied with the weights x1 into w111 plus x2 w121 plus x3 w131 plus x4 w141 plus bias. This whole summation is the output, is the input which we give to this hidden layer and that gets passed through the hidden layer. The hidden layer contains an activation function. After passing through that activation function, we get the output as this. A1 is the output of this hidden layer, A2 is the output of this hidden layer, and we have a bias. After multiplying A1 with W112, A2 with W122 plus bias, that is given as input to the output layer, and we get the final output as this. Since output also has an activation function in it, let phi of x be the activation function for now. In this neural network, weights and biases are the parameters that the model learns during the training to make the accurate predictions. So first we need to know why do we use the RMS prop. Let us consider this figure 2. This is a contour plotting of a error function. At the start of the training of a model, our cost or error will be pretty high. Let it be at point A. From here, we try to calculate the negative descent and take another step in the direction of it, and let us suppose that we reach to point B, and in the next iteration we reach to point C, and so on. We will reach the local optima. What happens in performing gradient descent is will be optimize oscillating in the local optimas instead of going to the global optima, and while going to the global optima will take much more time. Using RMS propagation, we want to reduce that. To overcome this, we want slower learning rate in the vertical direction and the faster learning rate in the horizontal direction. So here is what we can do using RMS prop. RMS prop uses the concept of exponentially weighted average of the gradients. Here in minimizing the error function, what we do is we calculate the error function, the output which we get here, and the actual output, the difference between them is the error function. We define a error function with, with respect to the activation function used. If the activation function is sigmoid function, we consider the error function to be binary entropy loss function. After finding the error function, we update the weights and we calculate the error again. The error this time will be reduced. To get a reduced error, we have to update weights in a such a way that it is possible. To update weights, what we do is initial final weight is equals to initial weight minus b derivate the error function with respect to the weight which we need to update. So we calculate the updated weight and we try to minimize the error function specifically. In simple terms, we can say RMS prop uses an adaptive learning rate instead of treating the learning rate as a hyperparameter. This means that the learning rate varies over time. The RMS prop uses the same concept of the exponentially weighted average of gradient, same as gradient descent. But only difference here is the parameter. The learning rate will be varying with respect to time. And here this is the activation function used. Here we use the sigmoid activation function. The equation of sig function is 1 by 1 plus e power minus z is the sigmoid activation function. When sigmoid activation function is used to predict either 0 or 1, that is true or false type of questions, classification things, and binary entropy loss function is the error function which is used when sigmoid function is used as the activation function. And these are the equations which we use in RMS prop optimizer to update the weights. This is the moving average at a point t, and Vt minus 1 is the moving average at a point t1. Alpha is the decay rate. We consider value of alpha to be 0.9 generally, which means that 90% of the weightage is given to the previous value. The Vt minus 190% of the previous running average is considered, and only 10% is the squared gradient of the current batch. And after calculating the Vt, we update the weights. We update the weight using this equation. Vt is substituted here, and epsilon is considered to make sure that this v square root term will never goes to 0. Epsilon is some positive value, very small positive value. Beta is the learning rate. We consider beta to be 0.01. At 0.00, it is considered to be 0.001 because if it is more, then overfitting occurs. If it is less, underfitting occurs. That is the val- learning rate that should be considered based on the problem, but generally it is considered to be 0.001. Now the steps in writing the code. First is importing libraries and defining the activation function. Using this equation, we import the libraries, import numpy as np, and then we define the activation function and then the derivative of the sigmoid activation function. Here we are defining the neural network. We define the neural network using the giving the input size, hidden size, and the output size. We are initializing this, and some random weights are considered using this function random dot random, giving input size and the hidden size. Biases are taken some random values. Similarly, weights to the hidden layer and the biases are also considered. Some random values are considered. After that, we'll see will the feed forward neural network. Feed forward neural network is this is the code for feed forward neural network. Initially, we are doing np dot operation, that is multiplication input with the weight and bias is added. This is given to the hidden layer. After passing through the sigmoid, we get this a1 as the output, and that when multiplied with weights and bias adding biases, we pass again to the output layer as it contains sigmoid function, and we finally get this self.a2 as the output. After getting this value, we will also have the actual value of the output. By knowing those two, we'll calculate the error here using this binary cross entropy loss function. After that, back propagation is done. This is the code for back propagation. We weight, derivate the error with respect to weight, multiplied with learning rate, and the difference in weights is equated to this value, and the weights are updated. The next step is initializing RMS prop optimizer. As we have discussed before, learning rate is considered to be 0.001, decay rate to be zero point 0.9, and we initialize using these values, these parameters. To update the weights, we are considering these two equations which we have seen before. We are updating the moving average and then the weights are updated. This is the code for that, and this is the code for testing the neural network and training. Here we are initializing the neural networks. We are considering an example and initializing the neural networks. We are giving the number of epochs and learning rate and all. We are testing the neural network and we'll print the updated weights. Now let us see we'll run the code and see now. These are the references from which I've considered the values before. Check out these things if you need something related to that. And now we'll see the code of that. This is the code. We will run the code and see. Since we have considered those, we got the value of losses in after these many epochs, and we got the output. Now we'll finally print the updated weights. These are the updated weights. We initially considered the weights to be the computer system has generated something, and now these are the updated weights and biases. And this is what we do optimization of back propagation using RMS prop optimizer. I hope I've conveyed everything which I wanted to. Thank you.